In this video, I'll talk briefly about one of the research projects I participated in. So the high-level object of this project is to use mixed reality headset Quest 3 for semantic mapping or semantic labeling of an unobserved environment, where the data can also be used as VQA, so visual question answering purposes. There are already many state-of-the-art libraries and papers in this domain, such as VoxBlocks++ or Chimera Semantics or Semantic Fusion. And in their order of existence, they take inputs like RGBD data, or Chimera Semantics takes input as stereo vision data and IMU data, or Semantic Fusion also assumes accepts RGBD data. And our goal is to use Quest 3 instead of using these different sensors. And the output they yield is mainly truncated sign distance fields or voxel maps or meshes or circle maps, again in their order of existence here. And one fundamental thing is that they assume the environment is unobserved in the beginning. So Quest 3 seems like this, and it has 3 cameras, and we can access any of them, and we can access the RGB data of these cameras. But the problem is that the depth value is not accessible because of the privacy reasons of Meta, and we can also not access multiple cameras at the same time, which means if we don't have depth value, we cannot create RGBD images. And since we cannot access multiple cameras, then it's really hard to create stereo vision structure. So we slightly change our flow a little bit here. But what we can do is we can access the scanned scene mesh, and we can access the 3 degree of freedom pose of the headset in that scene. So our current flow is so first we assume actually the scene is semi-observed, so it's partially scanned, and we have a valid mesh, and we access it, and we access the camera stream and headset pose, and according to the RGBD data and our current localization position, we do semantic panoptic segmentation, and we raycast from each pixel onto the mesh, and we label the mesh with color encoding according to the class of the object which we segmented. And one optional step is that we can improve the mesh quality with the time. With better observations, we would achieve high quality or higher quality meshes. But for simplicity, for now, we assume that we are working on an enough quality mesh, let's say. So for panoptic segmentation, we use the Tektron 2 again by Meta, and the idea is to project so raycast from each pixel which we classify, and from each instance basically. From each pixel we raycast onto the mesh, and according to the instance we color encode the mesh, let's say. And so what I mean is from any object, from any pixel here, we are raycasting onto the mesh, and we are coloring this mesh vertex according to the instance class. And the first results seem like this. As you see, red is encoded for chair, and yellow is for screen, purple is for bench. This is a problem of the mesh here, because there's a television normally, but since it's reflective, it's really hard to create this as a mesh. And we process further the coloring and the mesh, and we solve some issues, and the final result seems like this, where we actually improve the mesh quality and the coloring quality. So in this project, I use ROS, Python, and Unity engine for developing apps, which will work on Quest 3. Um, and I use OpenGL for mesh processing.